Can machines see the birth of time? Tonight, we're going to explore the most powerful eye humanity has ever built, the James Webb Space Telescope. You've probably heard this name countless times in the news, seen its golden mirror in documentaries, maybe even glimpsed those stunning cosmic images flooding social media. But here's what most people don't realize. This isn't just a bigger telescope taking prettier pictures. It's a time machine that's literally watching the universe grow up, molecule by molecule, galaxy by galaxy. By the end of this journey, you're going to understand how we went from detecting individual organic molecules smaller than viruses to mapping structures billions of light years across, and why every single discovery is rewriting our understanding of how everything we know came to exist. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This is going to be extraordinary. The James Webb Space Telescope was launched in December 2021 after 3 decades of meticulous planning. 3 decades? Think about that for a moment. When engineers first began sketching the concepts that would become Webb, the internet was barely a whisper, cell phones were the size of bricks, and the Hubble Space Telescope hadn't even been launched yet. In July 2022, just months after Webb opened its golden eye, it revealed the deepest field ever captured, an image made by collecting light for an extraordinary amount of time, like leaving a camera open through an entire night to reveal stars invisible to the naked eye. But this wasn't just any photograph. This single image showed thousands of galaxies that had been completely invisible to us before, scattered across what appeared to be empty darkness. The telescope doesn't orbit Earth like Hubble does. Instead, it travels around the Sun at nearly 1 million miles from our planet, 4 times farther than the Moon. Picture that distance for a moment. If you could drive to the Moon at highway speed, it would take you about 4 months of continuous driving. Webb is 4 times farther out than that, floating in the cosmic deep, far from Earth's warmth and interference. Its primary mirror spans 21.5 feet in diameter, composed of 18 hexagonal segments, each one coated in gold. Gold because gold reflects infrared light better than any other practical material. Each segment was polished to perfection. If one of these mirrors were scaled up to the size of Earth, the largest imperfection would be only 6 feet tall. 5 layers of sun shield protect Webb's delicate instruments, keeping them at just 12 degrees above absolute zero, colder than anywhere naturally occurring in our solar system. This frigid temperature is essential because Webb sees in infrared light heat radiation invisible to our eyes. If the instruments were warm, they'd be blinded by their own heat, like trying to see stars while staring into a campfire. This infrared vision allows Webb to penetrate dense clouds of cosmic dust that have hidden stellar nurseries from us for millennia. More importantly, it can observe objects whose light has been stretched by the expansion of the universe during billions of years of travel. This stretching phenomenon, called redshift, occurs when light travels through expanding space itself. Think of it this way. Imagine you're listening to an ambulance siren as it drives away from you. The sound waves get stretched out, making the pitch lower. Light waves do something similar as the universe expands around them. The farther an object is from us, the more its light gets shifted toward longer, redder wavelengths. Webb can detect light from objects that formed just 400 million years after the Big Bang, 13.8 billion years ago. 400 million years might sound like an eternity, but in cosmic terms, it's practically infancy. If the universe's entire history were compressed into a single year, these early galaxies would have formed in early February. Now we're going to embark on a journey that will take us from the smallest molecules Webb can detect to the largest structures in the cosmos. This exploration begins at the scale of billionths of inches and will end by crossing billions of light-years of space. Along the way, you'll discover how each scale connects to the next, building the universe we see today, piece by extraordinary piece. Webb has detected organic molecules, methane, carbon dioxide, and water in disks around young stars. These discoveries matter because they reveal life's ingredients arising early in stellar formation, suggesting that habitable planets might be common throughout the galaxy. These molecules measure about 400 millionths of an inch across, containing just a few atoms chemically bonded together. To put this in perspective, if a single atom were the size of a tennis ball, a human cell would be larger than an entire football stadium. Yet Webb can identify these molecular signatures across hundreds of light-years of space. The telescope identified ethane for the first time outside our solar system, around the star ISO Chi I-147 located 600 light-years away. This young star has existed for only 1 to 2 million years and weighs just 11% as much as our Sun. Its spectrum, the rainbow breakdown of light that reveals chemical fingerprints, showed 13 different carbon-based molecules, the greatest chemical diversity ever observed in protoplanetary disks. These protoplanetary disks are structures of gas and dust that spin around newborn stars, the cosmic construction sites where planets will eventually form. Benzene, a molecule with 6 carbon atoms arranged in a ring, was detected 600 light-years from Earth. This discovery shows complex organic chemistry existing far from our planet, laying the potential foundation for life. Webb achieved something even more remarkable, detecting the methylcation, CH3+, for the first time ever. This molecule had been predicted theoretically in the 1970s, but never actually observed. CH3+ acts as a cornerstone of organic chemistry in space, reacting rapidly to form more complex molecules. It was found in protoplanetary disk D203-506, located 1,350 light-years away in the Orion Nebula. Intense ultraviolet radiation from nearby massive stars provides the energy needed to create this crucial molecule. Ironically, ultraviolet radiation that normally destroys complex molecules can actually create CH3+ under certain conditions. Webb detected polycyclic aromatic hydrocarbons, large molecules with multiple carbon rings. In galaxies 12 billion light-years distant, these complex molecules existed when the universe was only 1.5 billion years old, just 11% of its current age. The detection of organic molecules in such diverse environments suggests that life's chemical building blocks are abundant throughout the cosmos. The telescope detected sulfur dioxide for the first time in exoplanet atmospheres formed by photochemical reactions. Photochemical reactions occur when starlight provides energy to break apart and recombine molecules in a planet's atmosphere. This detection proves that Webb can identify not just static molecules, but active chemical processes happening in real time. Unidentified hydrocarbons were found in the atmospheres of brown dwarfs, objects between giant planets and small stars. This same molecular signature was previously detected by the Cassini probe in Titan's atmosphere, Saturn's moon. This marks the first time this molecule has been observed outside our solar system, connecting local chemistry with galactic chemistry. Cyanide compounds, including methyl cyanide and ethyl cyanide, were tentatively detected in protoplanetary disks around young stars. Cyanides play important roles in prebiotic chemistry, the chemistry that possibly preceded life's emergence on early Earth. These discoveries hint at the universe's remarkable chemical creativity. Webb has dramatically expanded our chemical inventory of the universe, cataloging molecules and environments previously completely inaccessible to observation. Think about this for a moment. We're literally reading the molecular signatures of worlds in formation, scattered across hundreds and thousands of light years, identifying the same carbon-based chemistry that flows through your own body. Now we expand our view from individual molecules to the larger structures where these molecules organize themselves into nascent planetary systems. Typical protoplanetary disks contain mass equivalent to 100 Earths worth of gas and dust, all spinning around newly formed stars. Webb has revealed disks with concentric rings and gaps, structures carved by the presence of forming planets plowing through the material like cosmic snowplows. The disk around HL Tau, 457 light-years away, shows multiple gaps, possibly indicating several Jupiter-sized planets. HL Tau is only 1 to 2 million years old, meaning giant planets can form surprisingly quickly after stellar birth, much faster than we previously thought possible. This disk spans approximately 13 billion miles in diameter, where 1 astronomical unit equals 93 million miles, the Earth-Sun distance. If the Sun were a basketball, Earth would be a peppercorn, located 88 feet away. The HL Tau disk would stretch for miles in every direction. Spiral arms have been detected in the disk around MWC 758, suggesting a massive planet is gravitationally disturbing the surrounding material. These gravitational perturbations act like waves in water when you throw a stone into a calm pond, ripples spreading outward through the cosmic material. Webb observed material falling from the outer stellar envelope directly into the protoplanetary disk around HL Tau. Stellar envelopes are clouds of gas and dust, still gravitationally collapsing onto the growing young star. It's like watching a cosmic river feeding into a spinning whirlpool. The telescope detected jets of gas shooting perpendicular to the disk plane at speeds of hundreds of miles per second. These jets occur when material falls onto the central star, but part of it gets ejected in collimated streams by stellar magnetic fields. Imagine a cosmic fountain powered by the star's magnetic grip on the infalling material. The object HH30 showed a disk viewed edge-on, appearing as a dark line cutting through the illuminated nebula around it. The shadow cast by the opaque disk blocks starlight, creating a distinctive pattern that reveals the system's geometry. It's like seeing a cosmic silhouette, the disk's profile, etched against the glowing background. This is where our journey truly begins to reveal its deeper meaning. Each of these observations connects to something larger, something that will carry us from these spinning disks to the planets they birth and eventually to the vast cosmic web that connects everything we've discovered. The molecules we've found, the disks we've mapped, they're all part of an unfolding story that spans from the smallest chemical bonds to the largest structures in the universe. But first, let's witness something extraordinary happening within these disks. Webb has revealed that dust grains gradually settle into the midplane of these spinning structures, a process called dust sedimentation. Picture it like snow falling through still air, except this cosmic snow has been falling for millions of years, slowly accumulating into a thin layer where planets will eventually be born. These grains start microscopic, smaller than the width of a human hair, but they don't stay that way. They collide and stick together, growing from 40 millionths of an inch to fractions of an inch, and eventually into pebbles, measuring inches and even feet across. This gradual growth of dust grains marks the very first stage of planetary formation, the same process that created every planet we know, including the one you're standing on right now. Think about that for a moment. The ground beneath your feet, the chair you're sitting in, the device you're using to listen to this. All of it began as microscopic dust grains floating in a disk around our young sun 4.5 billion years ago. Webb has observed something called the snow line in these protoplanetary disks, the distance from a star where water freezes into solid ice. Inside the snow line, water exists as vapor because of stellar heat, but beyond it, water condenses and freezes onto dust grains. For sun-like stars, the snow line typically sits between 186 million and 465 million miles from the star, roughly in the region where our asteroid belt orbits today. This might seem like an abstract detail, but it's actually crucial for life as we know it. Ice pebbles beyond the snow line can drift inward, delivering water that eventually forms oceans on rocky planets. Webb has confirmed this process by observing excess water vapor in the inner regions of compact disks. Compact disks are smaller and have more efficient pebble drift, delivering more icy material to the regions where rocky planets form. In contrast, extended disks with multiple gaps trap pebbles in distant rings, limiting water delivery to inner regions. It's like the difference between a smooth slide and one with barriers. Some configurations are simply better at delivering life's essential ingredients to where they're needed most. Webb made a discovery that solved a decades-old puzzle. The telescope revealed that disks around stars with few heavy elements last much longer than theoretically predicted. In the small Magellanic Cloud galaxy, disks around young stars persist for 20 to 30 million years, 10 times longer than expected. This discovery resolved an enigma that had puzzled astronomers since 2003, when Hubble detected a giant planet around a star almost as old as the universe itself. Ancient stars have very few heavy elements because they formed when the universe was chemically primitive, containing mainly hydrogen and helium. Theories predicted that metal-poor disks would be quickly dispersed by stellar radiation in less than 1 million years. But Webb proved these disks last long enough to form massive planets, even in environments poor in heavy elements. The explanation may be that stars in metal-poor environments form from larger clouds, creating more massive and long-lived disks. More massive disks have more material that needs to be dispersed, extending the time available for planetary formation. It's like the difference between trying to blow away a handful of dust versus a pile of sand. The more material you have, the longer it takes cosmic winds to scatter it. Webb detected unexpectedly abundant carbon dioxide in the disk around star Xu-10, located 5,550 light-years away. This disk shows low water content but high carbon dioxide content, a chemical pattern opposite to what's normally observed. The star resides in star formation region NGC 6357, where intense ultraviolet radiation from massive stars alters disk chemistry. Unusual isotopes of carbon and oxygen were detected, including carbon-13, oxygen-17, and oxygen-18 enriched in the carbon dioxide. Isotopes are versions of elements with different numbers of neutrons in their nuclei, making them slightly heavier than their common versions. These isotopes might explain unusual isotopic signatures found in meteorites and comets from our own early solar system. Every rock that falls from space carries a chemical fingerprint of its birthplace. The isotopes Webb is detecting in distant disks might be the same ones embedded in the meteorites, sitting in museums around the world, remnants of our own solar system's formation. The disk around protostar HH30 showed that larger dust grains concentrate in the midplane, while smaller grains remain suspended higher up. This size stratification process is crucial for forming planetesimals, solid bodies measuring miles in diameter. Planetesimals are the building blocks of planets, growing through collisions and gravitational accretion until they become protoplanets. Picture it like a cosmic sorting machine where gravity and physics work together to organize material by size. The smallest particles stay aloft like cosmic dust motes, while larger pieces sink toward the center, where they can more easily find each other and stick together. Webb detected something remarkable in the Serpens Nebula, stellar jets all pointing in the same direction for the first time. Normally, protostars shoot jets in random orientations like cosmic sprinklers pointing every which way. But in this region, all the jets are tilted at the same angle, like diagonal rain driven by a consistent wind. This shared orientation suggests that a large-scale magnetic field or coordinated rotation is influencing regional star formation. The jets appear as bright red streaks in infrared images containing shocked molecular hydrogen and carbon monoxide. When gas jets collide with ambient gas at supersonic speeds, they create shock waves that heat the gas and make it glow. It's like seeing the universe's invisible magnetic architecture made visible through the alignment of these stellar fountains. Each jet traces magnetic field lines we cannot directly observe, revealing the hidden scaffolding that shapes how stars are born. What we're witnessing is the universe organizing itself on multiple scales simultaneously. While molecules assemble into complex chemistry, dust settles into planet-forming regions, stars align their jets along magnetic highways, and entire stellar nurseries coordinate their birth processes. Every scale influences the others in an intricate cosmic dance. The water that might someday fill alien oceans is being delivered right now by ice pebbles drifting inward through protoplanetary disks hundreds of light years away. The carbon dioxide enriching distant atmospheres carries isotopic signatures that will persist for billions of years. The magnetic fields aligning stellar jets are the same forces that will eventually shape the magnetospheres of future worlds. These disks are factories, manufacturing not just planets, but the very conditions that will determine whether those worlds can harbor life. Some will be water-rich, others carbon-rich. Some will form in magnetically active regions, others in cosmic quiet zones. Each combination of conditions creates different possibilities for the story that might unfold. Webb is showing us that planetary formation isn't a uniform process. It's wildly diverse, with each stellar nursery operating under its own unique conditions. The chemistry, the timing, the magnetic environment, the presence or absence of nearby massive stars. All of these factors influence what kinds of worlds emerge. And here's what makes this truly extraordinary. While we're watching these processes unfold in distant star-forming regions, similar events played out in our own solar system billions of years ago. The ice that became Earth's oceans, the carbon that became the foundation of life, the magnetic forces that still protect our atmosphere. All of these emerged from processes identical to what Webb observes happening right now across the galaxy. We are witnessing not just the birth of other worlds, but the ancient birth of our own. Every observation is a mirror reflecting our cosmic origins, showing us how we came to exist in a universe where dust becomes worlds and worlds might become homes. Now we expand our view once again from these protoplanetary construction sites to fully formed planetary systems orbiting distant stars. Webb has begun observing the atmospheres of exoplanets, planets orbiting stars beyond our sun, detecting their detailed chemical compositions with unprecedented precision. This is where the story becomes deeply personal, because we're not just cataloging distant worlds anymore. We're analyzing the air of alien skies, breathing spaces that might be similar to or utterly different from our own. The exoplanet WASP-39b, a gas giant located 700 light-years away, revealed definitive carbon dioxide in its atmosphere. This was the first clear and unequivocal detection of carbon dioxide on a planet outside our solar system, measured with spectral resolution that previous telescopes could only dream of achieving. WASP-39b has mass equivalent to 1/4 of Jupiter, but a diameter 1.3 times larger, making it extremely inflated and remarkably low in density. Picture a balloon filled with cotton candy, massive enough to be called a giant planet, yet so puffed up that it would float if you could somehow place it in a cosmic bathtub large enough. Its atmospheric temperature reaches 1,650 degrees Fahrenheit because it orbits its star at only 1/8 the distance between Mercury and our Sun. The planet completes an entire orbit in just 4 Earth days, gravitationally locked with one side always facing the star in perpetual day, the other in eternal night. But carbon dioxide was just the beginning. Webb also detected water, carbon monoxide, sodium, potassium, and sulfur dioxide in this planet's atmosphere. Sulfur dioxide forms through photochemical reactions when ultraviolet starlight breaks apart molecules and creates new chemical combinations. This detection proved that Webb can observe not just atmospheric composition, but active chemical processes happening in real time on alien worlds. Think about that for a moment. We're watching chemistry happen in the sky of a world so distant that light takes 7 centuries to reach us. We're observing molecular reactions occurring right now in an atmosphere that could contain our entire solar system. The exoplanet WASP-80b revealed definitive methane in its atmosphere, the first clear detection of methane by space telescopes. Methane is abundant in the giant planets of our solar system like Jupiter, Saturn, Uranus, and Neptune, but previously space telescopes, including Hubble, couldn't detect methane clearly in exoplanets where it should have been present. WASP-80b orbits a K-dwarf star with only 9% of our Sun's luminosity, maintaining cooler temperatures than other hot gas giants. The planet has approximately half of Jupiter's mass and orbits its star once every 3 Earth days. It's like a cosmic ice cube compared to the scorching furnaces we'd been studying before. Webb captured both the transit spectrum and the eclipse spectrum of this planet, measuring filtered light and emitted light separately. During transit, the planet passes in front of its star, and starlight filters through the planetary atmosphere, revealing absorbing molecules. During eclipse, the planet passes behind its star, allowing astronomers to measure infrared light emitted directly by the heated planetary atmosphere. Combining both methods, astronomers determined that methane definitely exists in WASP-80b, resolving a persistent mystery. It's like finally finding a missing piece of a cosmic puzzle that astronomers had been trying to solve for decades. The exoplanet WASP-107b showed east-west asymmetry in its atmosphere. The first time such asymmetry was observed during transit. Asymmetry means the eastern edge of the atmosphere has different properties from the western edge, possibly due to atmospheric winds carrying heat and chemicals around the planet. WASP-107b has extremely low density, only 1/10 of Jupiter's density, making its atmosphere exceptionally inflated. The planet's low gravity allows its atmosphere to extend much farther into space than atmospheres of more massive planets. It's like comparing a soap bubble to a marble. Both are spherical, but one is vastly more extended. Webb separated atmospheric signals from the eastern and western edges, revealing differences in temperature, clouds, and chemical composition. These observations indicate that atmospheric winds transport heat from the day side to the night side asymmetrically. The planet is gravitationally locked, so one hemisphere always faces the star in perpetual day, while the other experiences eternal night. Imagine standing on the border between day and night on such a world. Behind you, the sky blazes with starlight hot enough to vaporize metals. Ahead of you, eternal darkness stretches toward a horizon you could never reach. And above you, winds howling at thousands of miles per hour carry the heat of that eternal day toward the cold of endless night. But perhaps the most remarkable discovery came from 55 Cancri E, which provided the strongest evidence yet for an atmosphere around a rocky planet outside our solar system. This super-Earth has 8.6 times Earth's mass and orbits its star at just 1.4 million miles away. Close enough that it completes an orbit in only 18 hours, one of the fastest known orbits for any exoplanet. The dayside temperature reaches 5,000 degrees Fahrenheit, hot enough to melt rocks into a global magma ocean. Webb detected light absorption between specific wavelengths, indicating the presence of carbon dioxide or carbon monoxide in the atmosphere. Rocky planets so close to their stars usually lose their atmospheres rapidly due to intense stellar radiation. The atmosphere detected around 55 Cancri E is probably secondary, formed by gases continuously bubbling up from the underground magma ocean. While gases escape to feed the atmosphere, the magma ocean simultaneously reabsorbs gases, creating a dynamic cycle of replenishment. It's a world where the very rocks breathe, exhaling and inhaling in cosmic rhythm. Picture this alien landscape. The ground beneath your feet would be an ocean of molten stone, glowing orange and red like the inside of a blast furnace. The atmosphere above would shimmer with heat, filled with rock vapor and carbon compounds. The sky would be an alien color, perhaps deep red or orange, lit not by a distant sun, but by the molten landscape itself. These discoveries are rewriting our understanding of what constitutes a planet's atmosphere. We once thought atmospheres were simply gas envelopes around solid worlds. Now we know they can be dynamic systems where solid planets exhale their own substance into space, where winds reshape chemistry in real time, where the boundary between rock and gas becomes beautifully blurred. Each of these worlds tells a story about conditions that could exist nowhere in our solar system. WASP-39b, with its carbon dioxide clouds and sulfur chemistry, WASP-80b with its methane signatures in the light of a dim red star, WASP-107b with its asymmetric winds, 55 Cancri E breathing rock vapor into space. And these are just the beginning. Webb has characterized over 70 exoplanet systems in just 3 years of operation. The Hubble telescope took 34 years to study approximately 70 exoplanets, mainly detecting water in some atmospheres. Webb has surpassed Hubble's entire legacy of exoplanet characterization in a fraction of the operational time. What we're witnessing is the dawn of a new era in astronomy. For the first time in human history, we can analyze the chemical composition of alien skies in detail. We can watch weather patterns on worlds hundreds of light years away. We can identify the molecular signatures that might hint at habitability or detect the exotic chemistry of worlds unlike anything in our cosmic neighborhood. Every spectrum Webb captures is like receiving a chemical telegram from another world. Each absorption line tells us which molecules are present, their abundance, their temperature, their motion in alien winds. We are reading the atmospheric stories of worlds we will never visit, understanding their skies through the language of light. The implications extend far beyond simple curiosity. These atmospheric studies are teaching us how planets work, how chemistry operates under extreme conditions, how the delicate balance of temperature, pressure, and composition determines whether a world might harbor the processes we associate with life. While gases escape to feed the atmosphere, the magma ocean simultaneously reabsorbs gases, creating a dynamic cycle of replenishment. The exoplanet ʻOumuamua 561b provided even stronger evidence of rocky atmosphere, challenging assumptions about ultra-hot super-Earths. This planet completes an orbit in just 10.5 hours, making it a member of the rare class of ultra-short period super-Earths. Imagine a world where a year is shorter than your workday. The extreme proximity places the dayside at temperatures sufficient to vaporize rocks, creating an atmosphere of rock vapor. Scientists expected that intense stellar radiation would remove any atmosphere within a few million years, leaving bare rock exposed. but Webb measured day-side temperature consistent with heat redistribution, suggesting an atmosphere transporting energy around the planet. This planet must have formed in a chemical environment very different from solar system planets, poor in volatile elements. It's a world where the very definition of atmosphere expands, not just gases from outgassing or impacts, but the planet itself becoming its own sky. Picture standing on the day side of TOI 561b. The ground beneath you would glow white-hot, radiating heat like the surface of a star. The air you'd breathe, if such a thing were possible, would be vaporized rock, silicon, aluminum, iron, and magnesium floating as gas molecules. The horizon would shimmer not with water vapor like Earth's deserts, but with the ghostly forms of evaporated mountains. The exoplanet K2-18b revealed methane and carbon dioxide with high confidence, along with possible detection of dimethyl sulfide. K2-18b has 8.6 times Earth's mass and orbits an M-dwarf star at a distance compatible with liquid water on its surface. The equilibrium temperature is similar to or slightly cooler than Earth's, depending on detailed atmospheric properties. The absence of ammonia and carbon monoxide, combined with abundances of methane and carbon dioxide, rules out a mini Neptune with hydrogen-dominated atmosphere. The observations are consistent with a Hycean world, a hypothetical type of planet with a liquid water ocean beneath a hydrogen-rich atmosphere. Dimethyl sulfide, if confirmed, would be especially interesting because on Earth it's produced only by marine biological processes. Tiny marine organisms release this molecule as they live and die, creating a chemical signature that persists in our atmosphere. Finding it around another star could represent our first detection of active biology beyond our solar system. However, the detection of dimethyl sulfide remains tentative and requires additional observations for definitive confirmation before any conclusions about life can be drawn. Science demands caution when approaching such extraordinary claims, but the possibility hangs in the cosmic air that we might be detecting the breath of alien life carried on stellar winds across hundreds of light years. Think about what this means. We might be looking at a world where life could exist not on the surface like Earth, but in vast oceans beneath thick hydrogen atmospheres. An alien biosphere operating under conditions completely unlike anything we know, yet potentially detectable from hundreds of light years away through the molecular signatures it releases into its planet's sky. Imagine alien oceans underneath skies of pure hydrogen, where strange life forms might produce the same dimethyl sulfide molecules that float above Earth's seas. These hypothetical organisms would live under pressures and in chemical environments completely foreign to earthly life, yet they might share the same basic chemistry that betrays their existence to our distant telescopes. But perhaps the most extraordinary atmospheric discovery came from WASP-17b, where quartz clouds were detected. These clouds form through condensation of silicon and oxygen atoms in the atmosphere. WASP-17b orbits its star at 1,300 light-years distance, with one side permanently illuminated and the other in perpetual darkness. Quartz crystals appear and disappear continuously as silicon and oxygen evaporate and condense in the dynamic atmosphere. This is the first detection of clouds identified through specific molecular bonds rather than indirect inference through absent gases. Different molecules and clouds absorb specific wavelengths of light, creating unique and identifiable spectral fingerprints. Picture this alien sky. Clouds made of actual crystals floating through an atmosphere hot enough to vaporize silicon. Rain that isn't water, but liquid quartz, condensing and evaporating in endless cycles. A world where gemstones float through the air like terrestrial snowflakes. On the day side, temperatures reach thousands of degrees Fahrenheit, hot enough to vaporize rock into its component atoms. Silicon and oxygen mix in the superheated atmosphere, then drift toward the night side where temperatures drop enough for these atoms to condense into tiny quartz crystals. These microscopic gems form clouds that drift back toward the day side, where they evaporate again in an eternal cycle. Webb has revolutionized exoplanet atmospheric characterization, observing more than 70 systems in just 3 years of operation. The Hubble telescope took 34 years to study approximately 70 exoplanets, mainly detecting water in some atmospheres. Webb has surpassed Hubble's entire legacy of exoplanet characterization in a small fraction of operational time. What we're witnessing is the birth of a new branch of astronomy, alien meteorology. We're studying weather patterns on worlds that circle foreign stars, tracking storms made of exotic materials, watching seasons change on tidally locked worlds where one side always faces the star. Each of these discoveries forces us to expand our conception of what a planet can be. We once imagined worlds as variations on familiar themes, rocky like Earth and Mars, gaseous like Jupiter and Saturn. Now we know of planets with diamond rain, quartz clouds, rock vapor atmospheres, and possibly even biological signatures in the skies of distant water worlds. The diversity is staggering. Some planets orbit their stars in hours, others in centuries. Some are so hot that rocks evaporate, others so cold that their atmospheres freeze solid. Some have skies filled with exotic chemistry we never imagined. Others might harbor the familiar chemistry of life. Consider the range of atmospheric phenomena Webb has revealed. Planets where the air is made of vaporized metal, worlds where crystal clouds drift through hydrogen skies, super-Earths exhaling rock vapor into space, and possible ocean worlds releasing the molecular signatures of life. Each spectrum tells a story written in light. The biography of a world told through the wavelengths its atmosphere absorbs and emits. Every peak and valley in these spectral measurements represents molecules interacting with starlight, chemical processes unfolding in alien skies, weather patterns unlike anything in our solar system. The implications reach far beyond cataloging exotic atmospheres. These studies are teaching us how planets work under extreme conditions, how chemistry operates in environments we never imagined, how the delicate balance of temperature, pressure, and composition determines whether a world might harbor the processes we associate with life. Some of these worlds challenge our basic understanding of planetary physics. How can a planet maintain an atmosphere when its surface is hot enough to vaporize rock? How do quartz clouds form and persist in the dynamic chaos of tidally locked worlds? How might life adapt to hydrogen-rich atmospheres above liquid water oceans? But we're not done expanding our view. Now we scale up once again from individual planets to stellar nurseries where entire generations of stars are being born and dying in gigantic cosmic foundries. Webb has penetrated dense clouds in the Serpens Nebula, revealing protostars completely invisible in visible light due to dust. The Serpens North region previously appeared as indistinct smudges, or was completely invisible at optical wavelengths to Hubble. The telescope revealed internal structures of dense molecular clouds where individual stars are being born from gravitationally collapsing cores. Bright red molecular jets in infrared images mark where gas ejected by protostars collides with surrounding ambient gas. These jets stretch for light years, carved through space by magnetic fields and stellar winds. They appear as brilliant scarlet streaks against the dark backdrop of the nebula, like cosmic contrails marking the birth of new suns. Webb detected extremely young stars still wrapped in dense envelopes of gas and dust that feed their continued growth. These embryonic stars are only a few thousand years old, cosmic babies on stellar timescales. For context, our Sun is 4.6 billion years old, so these protostars have existed for only 0.0001% of the Sun's age. If the Sun's lifetime were compressed into a single year, these protostars would have been born just 30 seconds ago. They're so young that they're still growing, still accumulating mass from the cosmic material around them, still learning how to be stars. Webb identified clusters of protostars where dozens or hundreds of stars are forming simultaneously within the same molecular cloud. It's like watching a cosmic maternity ward, where stellar births happen not one at a time, but in great waves of creation. The entire region glows with the infrared heat of formation, a stellar nursery bustling with activity. The gravitational collapse that creates these stars generates tremendous heat. As gas and dust fall inward under their own gravity, the material heats up, eventually becoming hot enough to trigger nuclear fusion in the core. But this process takes time, millions of years for the largest stars, tens of millions for smaller ones. The IC 348 stellar cluster revealed brown dwarfs with masses as small as 3 to 4 times Jupiter's mass. Brown dwarfs are objects that form like stars but lack sufficient mass to initiate hydrogen fusion in their cores. Think about this for a moment. These are failed stars, objects that tried to become suns but fell just short of the nuclear threshold. They burn through their initial gravitational energy and then slowly fade over billions of years, neither true stars nor planets, but something entirely different. With mass below 75 times Jupiter's mass, or 7.5% of solar mass, objects cannot maintain stable hydrogen fusion. These extremely small brown dwarfs in IC 348 have only 3 to 4 times Jupiter's mass, approaching the lower limit of stellar formation. The discovery challenges theories of star formation, suggesting that the process can create objects much smaller than previously predicted. It's as if the universe's stellar factory can run on minimum settings, creating dwarf versions of stars that hover on the boundary between planets and suns. Mysterious hydrocarbons detected in these brown dwarf atmospheres match the same spectral signature seen on Titan, Saturn's moon. We're finding the chemistry of our own solar system replicated in the atmospheres of failed stars hundreds of light years away. Every observation reveals new connections. The molecules we studied in protoplanetary disks are the same ones floating in brown dwarf atmospheres. The chemistry that creates planets also operates in these stellar borderlands. The processes that built our solar system are universal, operating throughout the galaxy on countless scales. What's emerging is a picture of the cosmos as an interconnected chemical laboratory. Stars, planets, moons, brown dwarfs, and protoplanetary disks all share common chemistry, common physics, common origins. The carbon in your body was forged in stellar cores, the water in your cells condensed in molecular clouds. The oxygen you breathe was exhaled by dying stars. These stellar nurseries are the cosmic foundries where the elements of future worlds are being assembled. Each protostar represents not just a future sun, but a future solar system. Some will form planets like Earth. Others will create exotic worlds with quartz clouds and rock vapor atmospheres. Still, others will birth brown dwarfs that bridge the gap between stars and planets. Brown dwarfs are objects that form like stars but lack sufficient mass to initiate hydrogen fusion in their cores. With mass below 75 times Jupiter's mass, or 7.5% of solar mass, objects cannot maintain stable hydrogen fusion. These extremely small brown dwarfs in IC 348 have only 3 to 4 times Jupiter's mass, approaching the lower limit of stellar formation. The discovery challenges theories of star formation, suggesting that the process can create objects much smaller than previously predicted. It's as if the universe has found a way to make stars in miniature, pushing the boundaries of what we thought was possible in cosmic construction. Mysterious hydrocarbons detected in the atmospheres of these brown dwarfs match the same spectral signature seen on Titan, Saturn's moon. We're finding the chemistry of our own solar system replicated in the atmospheres of failed stars hundreds of light years away, suggesting that certain molecular processes are truly universal. But now Webb takes us beyond stellar birth to stellar death. The telescope revealed unprecedented details of the Cassiopeia, a supernova remnant, located 11,000 light-years away in the constellation Cassiopeia. This supernova exploded approximately 340 years ago, expanding stellar debris at speeds of thousands of miles per second. Picture the moment of that explosion. A star 20 times more massive than our Sun reached the end of its nuclear fuel, and its core collapsed in less than a second. The resulting shockwave tore through the star's outer layers, creating an explosion so violent that for weeks it outshone every other star in its galaxy. The remnant now spans about 60 trillion miles in diameter, continuously expanding as ejected material collides with interstellar gas. Complex filaments of gas at different temperatures reveal the physics of shockwaves as ejected material sweeps through the interstellar medium. It's like a cosmic archaeological site, preserving the moment of stellar death in expanding rings of superheated plasma. Webb detected specific heavy elements scattered by the explosion throughout interstellar space: oxygen, sulfur, calcium, and iron. Heavy elements are forged only in stellar cores during nuclear fusion or in the extremely energetic explosions of supernovas. Every atom heavier than hydrogen and helium in your body was created in the nuclear furnace of a star. Think about this deeply. Every atom of iron in your blood was created in a supernova that exploded before our solar system formed. Every atom of calcium in your bones was forged in massive stars that lived and died in previous stellar generations. You are literally made of star stuff, the processed remains of ancient suns that gave their lives to seed the universe with the elements needed for planets and life. Supernovas release energy equivalent to approximately 10, followed by 44 zeros joules, equivalent to 100 trillion Hiroshima bombs. This energy is sufficient to briefly outshine entire galaxies containing billions of stars for several weeks. If a supernova exploded 8.5 light-years from Earth, the distance to Sirius, it would appear as bright as the sun in our sky. The violence is almost incomprehensible. In the span of seconds, a star tears itself apart with such force that the explosion can be seen across billions of light-years. The shockwave travels at 10% the speed of light, compressing and heating everything in its path. Behind it, the stellar core either becomes a neutron star, matter so dense that a teaspoon would weigh as much as Mount Everest, or collapses completely into a black hole. These cosmic explosions are essential for life. Without supernovas scattering heavy elements throughout space, the universe would contain only hydrogen and helium. No carbon for organic chemistry, no oxygen for water, no silicon for rocky planets, no iron for blood. Every element that makes life possible was forged in stellar cores and distributed by stellar explosions. Now we expand our perspective once more, from individual stars to entire galaxies. Webb observed individual stars in nearby galaxies with resolution impossible for any previous telescope, including Hubble. The FANGS program observed 19 nearby spiral galaxies in unprecedented infrared detail, revealing individualized stellar structures. The telescope cataloged approximately 100,000 stellar clusters in these 19 galaxies, the largest catalog ever compiled by a single program. Stellar clusters typically contain hundreds to thousands of stars, born together from the same molecular cloud and gravitationally bound. They're like stellar families, groups of suns that formed in the same cosmic nursery and now travel through space together. The bright spiral arms in these galaxies contain active star formation regions where gas collapses to form new generations of stars. These arms aren't solid structures, but density waves that sweep around the galaxy, compressing gas and triggering star birth. It's like a cosmic traffic jam that creates stars instead of delays. Interstellar dust absorbs ultraviolet and visible light from young stars and re-emits that energy at infrared wavelengths. Webb sees this infrared emission directly, revealing dust structures invisible to Hubble and ground-based optical telescopes. While Hubble sees dark regions where starlight is blocked by dense interstellar dust absorption, Webb peers right through, seeing the warm glow of the dust itself. Combining data from Webb and Hubble, astronomers construct complete images showing stars, gas, and dust simultaneously in galaxies. It's like having both X-ray and visible light views of the same scene. Each reveals different aspects of the same cosmic structures. Galaxy NGC 628 sits 32 million light-years distant, meaning the light we observe today departed when primitive primates inhabited Earth. Galaxy NGC 1672 is located 60 million light-years away, so the light we observe left when dinosaurs still dominated our planet. Galaxy NGC 1087 lies 80 million light-years distant, its light traveling during the period when small mammals began diversifying after the dinosaur extinction. These distances reveal that observing the cosmos means literally looking backward in time through cosmic historical windows. The farther the observed object, the older the light we receive, and the farther back we travel into the universe's history. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star beyond our sun, you see it as it was 4.2 years ago. But these nearby galaxies are just the beginning of our temporal journey. The light from NGC 1672 began its journey when Earth was a completely different world. No grass covered the landscape. Flowering plants hadn't evolved yet. The continents sat in different positions. The very air had a different composition. Think about the profound implications. We're not just seeing distant objects, we're seeing the past directly. Every photon Webb collects is a messenger that has traveled across space and time, carrying information about cosmic events that happened when Earth was young, when life was primitive, when the planet itself was still forming its modern character. The galaxy we observe today, as it appears in Webb's images, actually represents how it looked when these photons began their journey millions of years ago. In the time those photons have been traveling toward us, entire species have evolved and gone extinct on Earth. Mountain ranges have risen and eroded. Continents have drifted thousands of miles. These observations demonstrate that astronomy is fundamentally archaeology. We don't study the universe as it is, but as it was. Every telescope is a time machine, every observation a glimpse into cosmic history. The deeper we look into space, the further back in time we travel. And now we're about to take the deepest journey yet. We expand dramatically in scale from nearby galaxies to primitive galaxies formed in the extremely distant and young universe. Webb has detected galaxies existing only 400 to 700 million years after the Big Bang, when the universe was only 3 to 5% of its current age. If the universe's history were compressed into a single year, these primitive galaxies would have formed in mid-January when the cosmic year was still young, and the universe was a vastly different place. These early galaxies appear surprisingly large and mature, contradicting models of galaxy formation based on the standard cosmological paradigm. 6 candidate galaxies discovered initially seemed too massive to have formed so quickly after the universe's birth. Each candidate galaxy contains stellar mass equivalent to more than 10 billion times our Sun's mass. One candidate galaxy appeared even more massive than the entire Milky Way, despite having had billions of years less time to form stars. If the masses were correct, these galaxies would have needed to convert nearly 100% of their available gas into stars, an efficiency that borders on the impossible. Typically, galaxies convert at most 10% of available gas into stars, with the remainder staying gaseous or being expelled by stellar winds and radiation. 100% conversion is technically at the extreme limit of what's theoretically possible, but would require conditions drastically different from those observed locally. Think about what this means. These ancient galaxies would need to be perfect stellar factories, converting every single atom of available hydrogen and helium into stars with no waste, no loss, no inefficiency. It's like imagining a car that burns fuel with perfect efficiency. Theoretically possible, but requiring conditions that don't exist in the real world. Subsequent spectroscopic observations revealed that supermassive black holes in some of these galaxies were artificially increasing their brightness. Supermassive black holes rapidly accreting material create extremely luminous accretion disks, quasars, that can outshine entire galaxies. Accretion disks are structures of gas spiraling toward the black hole, heating to millions of degrees through friction and compression. Picture a cosmic whirlpool where matter doesn't just fall into the center, but spirals inward, heating up so intensely that it glows brighter than billions of stars. This additional brightness made some galaxies appear to contain more stars than they actually possessed, partially solving the initial enigma. However, a less severe problem persists. There are still approximately twice as many massive galaxies in the early universe as predicted by our models. It's as if the cosmic factory was running at double speed in the universe's youth, producing mature galaxies faster than we thought possible. One possible explanation is that stars formed more rapidly in the early universe than in the current era. Perhaps early galaxies were more efficient at converting gas into stars before stellar radiation heated and expelled the gas. The early universe was denser, hotter, more chaotic, conditions that might have accelerated the pace of stellar birth. Imagine the early universe as a pressure cooker of star formation. With matter packed more tightly together, with higher background temperatures, with different chemical compositions, the processes that create stars might have operated under very different rules. Webb discovered quiescent galaxies in the early universe. Galaxies that mysteriously stopped forming new stars very early in cosmic history. One dead galaxy was observed when the universe was only 700 million years old, ceasing star formation just 100 million years after its birth. The reason why young galaxies abruptly cease star formation remains unexplained by current theoretical models. It's like discovering that some cosmic engines simply turned themselves off for reasons we don't understand. What could cause a galaxy to stop making stars when it should be in the prime of stellar production? Webb's discoveries include galaxies called red monsters, ultra-massive galaxies, formed surprisingly early in the universe. These galaxies already contained stellar masses comparable to the current Milky Way when the universe was only 1.9 billion years old. Spectroscopic confirmation using Webb's infrared capabilities validated the distances and masses of these extreme galaxies. We're not dealing with observational errors or measurement mistakes. These ancient giants really existed when the cosmos was still in its infancy. The galaxy Firefly Sparkle, discovered at 600 million years after the Big Bang, has mass similar to the Milky Way at the same cosmic epoch. This galaxy contains 10 distinct stellar clusters, each examined individually thanks to gravitational lensing amplification. Gravitational lensing occurs when the mass of intervening galaxies deforms spacetime, magnifying and distorting light from more distant objects. It's like having a cosmic magnifying glass created by Einstein's relativity. Massive objects literally bend the fabric of space and time, creating natural telescopes that allow us to see farther and in greater detail. The galaxy cluster MAXJ 1423 acts as a natural lens, magnifying the Firefly Sparkle galaxy by up to 16 times its apparent size. Without gravitational amplification, Firefly Sparkle would be just an indistinguishable point of light, impossible to study in any detail. Thanks to this cosmic lens, we can examine its individual stellar clusters as if we were much closer. Think about this remarkable coincidence. A massive galaxy cluster happened to sit at exactly the right distance and position to act as a magnifying lens, allowing us to peer deep into cosmic history and examine the detailed structure of an infant galaxy. It's as if the universe conspired to give us a perfect view of its own youth. Webb discovered stellar clusters in the cosmic gem's arc when the universe was only 460 million years old. This marks the first discovery of gravitationally bound stellar clusters in an infant galaxy less than 500 million years old. 5 young and massive stellar clusters were detected, contributing most of the galaxy's ultraviolet light. These clusters are significantly denser than nearby stellar clusters, containing more stars in smaller volumes. They're like cosmic cities where stars are packed together much more tightly than in our galactic neighborhood. The detection provides direct insight into the initial stages that might eventually form the globular clusters observed in mature galaxies. Globular clusters in the Milky Way contain ancient stars 12 to 13 billion years old, relics of intense early star formation. These ancient stellar clusters in our own galaxy are like cosmic archaeological artifacts. They preserve star formation from the universe's youth when conditions were very different from today. Some of the stars in Milky Way globular clusters are nearly as old as the universe itself, formed when the cosmos was still learning how to make galaxies. Webb identified the first filaments of the cosmic web, the large-scale structure of the universe, existing 830 million years after the Big Bang. A filament of 10 galaxies extends across 18 trillion miles, anchored by a luminous quasar with an active supermassive black hole. This early filament will eventually evolve into a massive galaxy cluster containing thousands of gravitationally bound galaxies. We're seeing the cosmic web in its infancy, the skeletal framework upon which all large-scale structure would eventually grow. The cosmic web connects galaxies along filaments of dark matter, interspersed by vast voids containing few galaxies. Picture the universe as a three-dimensional spider web, with galaxies strung along the threads like dewdrops, separated by enormous empty spaces where virtually nothing exists. Dark matter constitutes approximately 27% of the universe's energy density, but doesn't emit light detectable by telescopes. Its presence is inferred through gravitational effects on visible matter, gravitational lensing, and galaxy rotation velocities. We know dark matter exists not because we can see it, but because we can observe its gravitational influence on everything we can see. Imagine an invisible scaffolding that shapes the entire universe. Dark matter provides the gravitational framework along which normal matter flows, creating the cosmic web of filaments and voids. Without dark matter, the universe would look completely different, perhaps just a uniform soup of gas with no galaxies, no stars, no planets. The cosmic web filaments contain dark matter, forming the gravitational structure along which normal matter collapses to form galaxies. It's like watching the universe organize itself according to an invisible blueprint written in gravitational forces. Every observation Webb makes of these early structures reveals the universe in a state of rapid assembly. Galaxies forming faster than expected, black holes growing to enormous sizes, stellar clusters packing together in dense configurations, cosmic filaments stretching across vast distances. The early universe was clearly a more dynamic, more intense, more rapidly evolving place than the relatively calm cosmos we observe today. Star formation rates were higher, galaxy growth was accelerated, black holes were feeding more voraciously. It's as if the entire universe was running in fast-forward mode. These discoveries challenge our fundamental understanding of cosmic evolution. If galaxies could grow so massive so quickly, if black holes could reach such enormous sizes, if stellar clusters could form so densely, then our models of how the universe develops over time need significant revision. We're witnessing the universe's rapid youth, a time when cosmic processes operated under different rules, when the pace of change was dramatically accelerated, when the foundations of everything we see today were being laid down in a cosmic construction boom. The light from these early galaxies has been traveling toward us for over 13 billion years, carrying information about cosmic conditions when the universe was radically different from today. Each photon is a time traveler, preserving a moment from the universe's youth and delivering it to our instruments across the vast gulf of space and time. Dark matter constitutes approximately 27% of the universe's energy density, but doesn't emit light detectable by telescopes. Its presence is inferred through gravitational effects on visible matter, gravitational lensing, and galaxy rotation velocities. We know it exists not because we can see it directly, but because we observe how it bends light, how it affects the motion of galaxies, how it shapes the large-scale structure of everything we can observe. Cosmic Webb filaments contain dark matter forming the gravitational structure along which normal matter collapses to form galaxies. Think of dark matter as the invisible skeleton of the universe, providing the framework upon which all visible cosmic architecture is built. Webb detected black hole winds in the early universe, jets of gas ejected by rapidly growing supermassive black holes. These winds travel at hundreds of miles per second, potentially suppressing star formation by expelling gas from the host galaxy. It's cosmic feedback at its most dramatic, black holes literally blowing away the very material that feeds star formation. Black holes observed by Webb in the early universe have masses between 600 million and 2 billion times our Sun's mass. For context, the black hole at the center of our Milky Way, Sagittarius A star, has a mass of only 4 million solar masses. These early universe monsters are hundreds of times more massive than the supermassive black hole in our own galactic center. The universe was less than 1 billion years old when these supermassive black holes had already grown to billions of solar masses. The mechanism by which black holes grew so massive so rapidly remains one of the greatest enigmas in contemporary astrophysics. Consider the impossibility of this growth rate. Black holes can only grow by accreting matter, but there are physical limits to how fast they can feed. Matter spiraling into a black hole heats up and radiates energy, creating radiation pressure that pushes against infalling material. This creates what astronomers call the Eddington limit, a theoretical maximum growth rate. Even growing at the Eddington limit continuously, starting from stellar mass black holes formed by the first generation of stars, these monsters shouldn't exist. They would need billions of years to reach their observed masses, but the universe was less than 1 billion years old when Webb observed them. Something extraordinary must have happened in the early universe to create these giants. Perhaps they formed directly from primordial gas clouds, skipping the stellar phase entirely. Perhaps the Eddington limit didn't apply under early universe conditions. Perhaps multiple black holes merged in rapid succession. We simply don't know. Webb observed protoclusters, precursors of massive galaxy clusters, in formative stages when the universe was only 650 million years old. 7 spectroscopically confirmed galaxies move at velocities exceeding 2 million miles per hour within a shared dark matter halo. These high velocities indicate that the galaxies are gravitationally bound and will eventually collide and merge to form a giant elliptical galaxy. The protocluster sits behind the Pandora cluster, magnified by gravitational lensing that allows detailed observation of distant objects. Galaxy clusters are the largest gravitationally bound structures in the universe, containing thousands of galaxies with masses equivalent to quadrillions of suns. The nearby Coma cluster, an example of a mature cluster, contains more than 1,000 large galaxies within a region spanning 120 trillion miles. The total mass of the Coma cluster equals approximately 1 followed by 15 zeros times our Sun's mass, a quadrillion solar masses. If you could somehow place our entire solar system out to Pluto's orbit inside a single atom, the Coma cluster would still contain more atoms than exist in a human being. Webb revealed that early galaxies were highly unstable, filled with clumps of gas and stars rather than smooth disks. Examining over 250 young galaxies existing when the universe was between 800 million and 1.5 billion years old, a pattern emerged. Gas movement within these galaxies showed chaotic turbulence instead of the ordered rotation observed in mature spiral galaxies like the Milky Way. Intense star formation and gravitational forces stirred the gas so violently that many galaxies struggled to establish stable rotation. Picture the difference between a calm lake and whitewater rapids. Modern galaxies rotate like serene lakes, with gas and stars following predictable orbital paths. Early galaxies were like cosmic rapids, with material churning chaotically, unable to settle into smooth, organized motion. Galaxies gradually transitioned from chaotic structures to stable structures as the universe evolved through billions of years. During the initial stages of cosmic history, the intensity of star formation and gravitational interactions prevented the formation of organized galactic disks. Yet Webb revealed well-organized disk galaxies existing surprisingly early, challenging expectations about the time needed for self-organization. Galaxy Rebels 25 shows an ordered disk similar to current galaxies, but is observed when the universe was only 700 million years old. This early organization suggests that some galaxy formation processes operated more efficiently in the early universe than predicted. It's as if some cosmic systems learned the rules of organization faster than others, developing mature structures while their neighbors remained chaotic. The Cosmos Webb program observes a single field of sky in extreme depth, detecting galaxy groups when the universe was 1.9 billion years old. This represents only 14% of the universe's current age, pushing the search for galaxy groups dramatically back in cosmic history. Galaxy groups are intermediate systems between isolated galaxies and massive clusters containing dozens of gravitationally bound galaxies. More than half of all galaxies in the universe belong to galaxy groups, making them critical for understanding typical galactic evolution. Belonging to a galaxy group can dramatically alter individual galaxy evolution through mergers and gravitational interactions with neighbors. It's like the difference between living alone in the countryside versus living in a busy neighborhood. The social environment profoundly shapes development. Cosmos Webb detected the most massive galaxy group in its observed field, using the Amico algorithm to identify gravitational groupings. The program yielded the largest sample of galaxy groups detected by Webb so far, revealing their distribution throughout cosmic history. Think about what we're witnessing. We're observing the universe, learning how to organize matter on the largest scales. Early protoclusters represent the first attempts at building massive structures. Galaxy groups show intermediate stages of cosmic organization. Modern clusters represent the mature result of billions of years of gravitational assembly. Every structure we observe existed in the past, when the universe operated under different conditions. The cosmic web was denser, star formation was more intense, black holes grew more rapidly, galaxies evolved faster. We're seeing a universe in its energetic youth before it settled into the more sedate patterns we observe locally. The light from these distant structures has been traveling toward us for most of cosmic history. Each photon carries information about conditions when the universe was radically different, hotter, denser, more chaotic, more rapidly evolving. We're not just studying distant objects, we're studying distant times. Every observation is a form of cosmic archaeology, revealing how the universe looked and behaved when it was young. The farther we look in space, the farther we travel back in time. And now we approach the very limits of what's observable. We've journeyed from individual molecules to galaxy clusters, from the smallest scales to structures spanning hundreds of millions of light years. But even these vast distances pale compared to what lies beyond. Now we reach maximum observable scales, where concepts of distance and time begin to lose intuitive meaning for human comprehension. The observable universe extends approximately 29 trillion miles in all directions from Earth currently. This distance exceeds the universe's age multiplied by the speed of light because space itself has expanded during 13.8 billion years. Space expansion over billions of years has carried distant objects farther than simple movement through static space would allow. Think about this carefully. Light from the most distant galaxies Webb observes began its journey when those galaxies were much closer to us. But while that light has been traveling toward us, the expansion of space itself has carried those galaxies farther and farther away. Galaxies observed by Webb at extreme redshifts are now physically located more than 180 trillion miles away. However, the light we observe was emitted when these galaxies were much closer before cosmic expansion dramatically separated us. If we could somehow stop the expansion and measure distances instantaneously, we would find an observable universe much larger than 13.8 billion light-years across. The cosmic horizon represents not just a distance limit, but a fundamental boundary beyond which information cannot reach us. The large-scale cosmic web organizes galaxies into filaments, walls, clusters, and voids in a three-dimensional foam structure. Filaments connect galaxy clusters, creating cosmic superhighways where galaxies flow along streams of dark matter. Picture the universe as a vast sponge. The solid parts of the sponge represent filaments and walls where galaxies congregate. The holes represent cosmic voids where very few galaxies exist. This foam-like structure extends throughout the observable universe. Walls are two-dimensional structures of clustered galaxies, the largest coherent structures known in the observable universe. The Sloan Great Wall extends approximately 8 trillion miles, one of the largest structures ever mapped. If the Milky Way were reduced to the size of a grain of rice, the Sloan Great Wall would stretch longer than 10 football fields. These cosmic walls represent the ultimate expression of gravitational organization, containing millions of galaxies arranged in sheet-like configurations. Cosmic voids are massive regions containing very few galaxies, typically measuring 600 trillion to 2.4 quadrillion miles in diameter. The Boötes Void, for example, contains only 60 galaxies in a volume that should contain approximately 2,000 based on average density. These voids aren't completely empty, but contain tenuous gas filaments and occasional isolated dwarf galaxies. Imagine cosmic deserts where galaxies are separated by distances so vast that light takes hundreds of millions of years to cross from one side to the other. If you lived in a galaxy within the Boötes Void, your night sky would be almost completely dark. Very few galaxies would be visible even with the most powerful telescopes. You would inhabit a cosmic wilderness, isolated from the rich galaxy neighborhoods that populate filaments and walls. Large-scale galaxy distribution reveals that the universe is remarkably uniform on scales above 1.8 trillion miles. This large-scale homogeneity validates the cosmological principle. The universe is approximately uniform when observed on sufficiently large scales. Webb's deep field captured thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Each galaxy in that image contains billions to trillions of stars, each star potentially hosting planets of its own. Replicating this deep field in all directions reveals an observable universe containing approximately 2 trillion galaxies. Think about this number for a moment. 2 trillion galaxies, each one a vast island universe containing billions or trillions of stars. Conservatively estimating 100 billion stars per typical galaxy, the observable universe contains approximately 200 sextillion stars. 200 sextillion is 200 followed by 21 zeros, 200,000 billion stars in just the observable portion of the cosmos. If each star were a grain of sand, we would need every beach on Earth plus several additional Olympic swimming pools to contain them all. The number transcends human comprehension so completely that analogies begin to lose meaning. Counting one star per second without stopping, it would take 6.3 million billion years to count all observable stars. This time exceeds the current age of the universe by a factor of approximately 500,000, completely transcending human scales of time. Imagine trying to count that high. If humanity had begun counting stars at 1 per second from the moment the first human ancestors appeared on Earth, we would have counted for only about 7 million years. We would need to count for 6.3 million billion years to finish. The task is so vast, it becomes almost meaningless. Webb revealed that the apparent simplicity of the universe on large scales conceals extraordinary complexity at all smaller scales. From molecules measuring billionths of inches to structures spanning trillions of miles, each scale exhibits unique phenomena governed by specific physics. Fundamental forces operate differently at different scales. Nuclear forces within atoms, electromagnetic forces in molecules, gravitational forces in cosmic systems. The universe is a hierarchy of scales, each governed by its own physical rules. The strong nuclear force holds quarks together within protons and neutrons, operating only at distances of femtometers, about 39 trillionths of an inch. At these impossibly small scales, the universe operates according to quantum mechanics, where particles exist in multiple states simultaneously, and certainty becomes probability. Electromagnetic force governs chemistry and atomic structure, operating efficiently from atomic scales up to everyday distances. This is the force that holds molecules together, that makes chemical bonds possible, that creates the chemistry of life. Gravity, although the weakest of the fundamental forces, completely dominates at scales of planets, stars, and galaxies. While electromagnetic forces become negligible across cosmic distances, gravity reaches across the entire observable universe, shaping the cosmic web itself. The hierarchy of cosmic scales reflects the hierarchy of fundamental forces organizing matter into progressively larger structures. Quarks form protons and neutrons, which form atomic nuclei. Nuclei capture electrons to form atoms. Atoms bond into molecules. Molecules organize into chemistry. Chemistry enables biology. Biology creates consciousness. Consciousness contemplates the cosmos. Webb demonstrated that understanding the universe requires examining not just individual objects, but connections between different scales. Molecules in protoplanetary disks eventually incorporate into planets. Planets orbit stars. Stars populate galaxies. Galaxies weave the cosmic web. Each level of organization emerges from interactions at smaller scales, creating increasing complexity through cosmic hierarchy. This progression reveals the universe as a deeply interconnected system rather than a collection of isolated objects. The carbon in your body was forged in stellar cores billions of years ago. The calcium in your bones was created in supernova explosions that occurred before Earth existed. The oxygen you breathe was exhaled by dying stars across cosmic history. You are not separate from the cosmos. You are the cosmos becoming aware of itself. Every atom in your body has traveled across space and time, participated in stellar fusion, witnessed cosmic evolution, and now temporarily organizes itself into the pattern that is you. The water in your cells condensed in molecular clouds, light years across. The iron in your blood was scattered by supernovas that briefly outshone entire galaxies. The very atoms that enable your consciousness to contemplate these cosmic scales were assembled in the nuclear furnaces of ancient stars. Webb's observations reveal this cosmic connectedness directly. The same molecules we find in distant protoplanetary disks exist in our solar system. The same physics that governs star formation in the Orion Nebula governed the birth of our Sun. The same gravitational forces that shape galaxy clusters also hold Earth in its orbit. Scale after scale, from the quantum realm to the cosmic web, everything connects. The uncertainty principle that governs quantum mechanics influences how atoms bond into molecules. Molecular chemistry determines how planets form from protoplanetary disks. Planetary formation affects stellar evolution. Stellar evolution shapes galactic chemistry. Galactic evolution influences the cosmic web. Webb has shown us that the universe operates as a single, integrated system where every scale influences every other scale. Understanding any part requires understanding its connections to the whole. Each level of organization emerges from interactions at smaller scales, creating increasing complexity through cosmic hierarchy. This scale progression reveals the universe as a deeply interconnected system rather than a collection of isolated objects. Webb's observations challenge not just scales of size, but also scales of time in cosmic history. The early universe revealed by the telescope operated at an accelerated pace, forming structures more rapidly than theories predicted. Galaxies, black holes, and stellar clusters matured in hundreds of millions of years instead of the billions expected. This acceleration suggests that the physics of the early universe functioned in subtly different ways from current local conditions. Perhaps the higher density of matter and energy in the young universe intensified structural formation processes. Think about this cosmic acceleration. It's as if the universe's construction crews were working double or triple shifts in its youth, building galactic skyscrapers and stellar cities at a pace that defies our understanding of cosmic construction timelines. Every process that takes billions of years today somehow compressed into hundreds of millions of years in the universe's youth. The cosmic microwave background radiation, remnant of the Big Bang, was millions of times more intense in the early universe than currently. This radiation heated intergalactic gas, affecting how and where stars and galaxies could form in early cosmic epochs. Imagine the early universe as a cosmic pressure cooker. Higher background temperatures, denser matter concentrations, and more intense radiation created conditions that could accelerate the very processes we observe happening more slowly today. The universe was like a forge running at maximum temperature, shaping cosmic structures with unprecedented speed and intensity. The density of matter in the early universe was extraordinary. If you took all the matter in a volume the size of our solar system today and compressed it into a space the size of Earth's orbit around the Sun, you'd approximate early universe conditions. Under such extreme density, gravitational collapse proceeded much more rapidly than in our current, more dilute cosmos. Stars formed faster, burned brighter, and died younger in this cosmic inferno. The first generation of stars were massive monsters, hundreds of times more massive than our Sun, burning through their nuclear fuel in just a few million years before exploding as supernovas that seeded space with heavy elements. The reionization period, when the first stars ionized neutral hydrogen throughout the universe, fundamentally transformed cosmic chemistry. Before reionization, the universe was filled with neutral hydrogen that absorbed ultraviolet light, making the universe opaque at those frequencies. For hundreds of millions of years after the Big Bang, the universe existed in what astronomers call the cosmic dark ages. No stars had yet formed to illuminate the hydrogen fog that filled all of space. It was a time of cosmic twilight, when matter existed but light could not travel freely. Picture this cosmic darkness. Imagine a universe where no starlight could penetrate more than a few light years through the hydrogen fog, where the only light came from the gradually cooling glow of the Big Bang itself, where matter existed in vast clouds, slowly condensing under gravity, but invisible to any hypothetical observer. During these dark ages, the seeds of future galaxies were already forming. Dark matter was clumping together under its own gravity, creating the scaffolding upon which the first stars and galaxies would eventually assemble. The universe was preparing for its cosmic dawn, organizing matter in the darkness like a stage crew setting props before the lights come up. After reionization completed approximately 1 billion years post-Big Bang, the universe became transparent, allowing light to travel freely. This transition from opaque to transparent marks a fundamental division between cosmic eras, a boundary that Webb is now observing directly. The telescope detects galaxies during and immediately after reionization, capturing the most dramatic transformation since the Big Bang itself. Observing these objects means literally witnessing the moment when the universe switched on its lights for the first time after the primitive dark ages. Picture that cosmic dawn. For hundreds of millions of years, space was dark and fog-filled. Then the first stars began to shine, their intense ultraviolet radiation gradually clearing the hydrogen fog like cosmic lighthouses cutting through primordial mist. Within a few 100 million years, the universe transformed from opaque to crystal clear. This wasn't a gentle sunrise, but a violent cosmic awakening. The first stars were so massive and hot that their ultraviolet radiation ripped electrons from hydrogen atoms across vast regions of space. Bubble-like cavities of ionized gas expanded around each early star, eventually overlapping and merging until the entire universe became transparent. Webb is showing us that very moment when clarity emerged from cosmic darkness. We're witnessing the universe's transition from its primitive, fog-bound state to the transparent cosmos we know today. Every early galaxy Webb observes is like a historical document from that cosmic transformation. As scale increases, it's not just size that becomes incomprehensible, but also the meaning of the concept of scale itself. At maximum cosmic scales, distinctions between here and there, now and then, begin to collapse under the weight of relativity and expansion. The observable universe represents not just a distance limit, but a fundamental boundary of what can be known through observation. Beyond the observable horizon exist regions of the universe whose light will never reach us, because space between us expands faster than light travels. These regions aren't just unknown, they're fundamentally unknowable through observational methods, separated by an absolute causal barrier. It's like being trapped inside an expanding bubble where information from outside can never penetrate, no matter how long we wait or how powerful our telescopes become. Consider the philosophical implications. There could be entire civilizations, entire galaxies, entire superclusters of galaxies beyond our observable horizon that we will never detect. The universe beyond our cosmic bubble could be completely different. Governed by different physical laws containing forms of matter and energy we can't imagine. The accelerating expansion of the universe, driven by mysterious dark energy, constantly increases this inaccessible region. Dark energy constitutes approximately 68% of the universe's total energy density, but its nature remains completely unknown. Dark energy acts like negative pressure, forcing acceleration of cosmic expansion instead of the deceleration expected from gravity alone. It's as if an invisible force is pushing the universe apart from within, overcoming gravity's attempt to pull everything together. Think about this cosmic irony. Gravity spent billions of years assembling matter into stars, galaxies, and galaxy clusters, but dark energy is winning the ultimate battle. The universe will continue expanding and accelerating until galaxies become so separated that beings in the far future will see only empty darkness beyond their own galactic group. At the universe's maximum scales, our ignorance about fundamental components, dark matter and energy, dramatically exceeds our knowledge. Dark matter and dark energy together constitute 95% of the universe's content, leaving only 5% as observable, ordinary matter. All light observed by every telescope in human history comes from just 5% of the cosmos's total energy content. This humbling realization reveals that the visible universe is merely a small foam on the surface of a much deeper cosmic ocean. Think about this profound limitation. Everything we can see, every star, every galaxy, every nebula, every planet, represents less than 5% of what actually exists. We're like deep-sea creatures who have never seen sunlight, trying to understand the ocean by studying the few particles that drift down to the depths. We've built increasingly powerful telescopes, developed sophisticated detection methods, launched observatories into space, and still we can only perceive 5% of cosmic reality. It's as if we're trying to understand a vast library by reading only the punctuation marks. Webb, despite its extraordinary capabilities, observes only this small visible fraction of total cosmic reality. However, even this fraction reveals complexity and beauty, sufficient to completely challenge human comprehension and theoretical models. The telescope's discoveries don't just answer ancient questions, they generate fundamentally new and deeper questions. Why did early galaxies organize so rapidly? How did supermassive black holes grow so massive so early? Why did some young galaxies abruptly cease star formation? What processes govern the efficiency of gas-to-star conversion? How do complex organic molecules form so easily in diverse interstellar environments? How common is prebiotic chemistry in the cosmos? Could life be far more widespread than we ever imagined? Are we observing the chemical signatures of biology in distant atmospheres? Every answer Webb provides opens 10 new mysteries. We thought we understood star formation timescales, but early galaxies formed too quickly. We thought we knew black hole growth rates, but early supermassive black holes were impossibly large. We thought galaxy evolution was gradual, but some early galaxies died unexpectedly young. The universe revealed by Webb is simultaneously more familiar and more alien than we expected. The same physics operates everywhere. The same chemistry creates similar molecules across cosmic distances. The same gravity shapes structures from planets to galaxy clusters. Yet the early universe operated under such different conditions that familiar processes produced unfamiliar results. We're discovering that our local cosmic neighborhood, the current universe around us, is actually quite unusual in cosmic history. The early universe was a more dynamic, more rapidly changing, more intensely active place. Modern cosmic conditions are relatively calm and slow by comparison. It's like discovering that the Earth you know, with its moderate climate, stable continents, and predictable seasons, is the geological equivalent of retirement age, and that young Earth was a violent, rapidly changing world of constant volcanic eruptions, unstable surfaces, and extreme weather. The molecules Webb detects in distant star-forming regions are the same ones that floated in the disk from which our solar system formed. The stellar clusters it observes in early galaxies are similar to the ones that formed our Sun and neighboring stars. The galactic mergers it witnesses in the distant universe resemble the collision that will eventually occur between the Milky Way and Andromeda. Yet these familiar processes operated under conditions so different from today that their outcomes challenge our theoretical understanding. It's cosmic familiarity operating under alien conditions, producing results that are simultaneously recognizable and impossible. Webb is showing us that the universe has a history, not just a timeline of events, but a genuine evolution, where the fundamental nature of cosmic processes has changed over time. The early universe wasn't just a younger version of today's cosmos. It was a qualitatively different place where the same physics produced dramatically different results. We're witnessing cosmic adolescence through Webb's infrared eyes, a time when the universe was more energetic, more chaotic, more creative, and more dangerous than the mature cosmos we inhabit today. A time when cosmic evolution proceeded at breakneck speed, when structures assembled rapidly, when the very nature of space and time were still settling into their modern patterns. These questions connect smaller scales of molecules with larger scales of galaxies through a causal chain of emergent phenomena. Understanding the universe requires not just cataloging objects, but comprehending how processes at one scale influence phenomena at other scales. Organic molecules in disks become ingredients for planets. Planets in habitable zones may develop life. Life can transform planetary atmospheres. Atmospheres transformed by life could theoretically be detected as biosignatures in spectra of distant exoplanets. Webb is beginning to search for these biosignatures, although definitive detection of extraterrestrial life remains beyond current capabilities. Even without detecting life, revealing the abundance of organic molecules and potentially habitable planets transforms our understanding of whether life is rare or ubiquitous. If the chemical building blocks of life are widespread and habitable planets are common, the implications for life's prevalence become profound. Consider what Webb has already shown us. Organic molecules floating in the atmospheres of brown dwarfs hundreds of light years away. Water, methane, and complex hydrocarbons in the disks where planets form. The same chemistry that flows through your body operating throughout the galaxy, perhaps throughout the universe. The universe revealed by Webb is one where conditions for life aren't extraordinarily rare, but possibly common across billions of worlds. This possibility recontextualizes humanity's position, not as occupants of a unique and special planet, but as representatives of a potentially common phenomenon. Think about this shift in perspective. For centuries, we wondered if we were alone. Now Webb suggests we might be asking the wrong question. Instead of "Are we alone?" perhaps we should ask, "How common is life?" And why haven't we found our cosmic neighbors yet? Simultaneously, the incomprehensible scale of the cosmos emphasizes how isolated we are, even if life is abundant throughout the universe. The nearest galaxies are millions of light years away, distances that completely challenge any conceivable travel technology. Even traveling at the speed of light, it would take 2.5 million years to reach Andromeda, the nearest large galaxy to the Milky Way. Interstellar travel within our own galaxy faces distances measured in light years, where the nearest star lies 4.24 light years away. Voyager 1, the most distant human-made object, would take 73,000 years to reach Proxima Centauri at its current speed. And Proxima Centauri is practically next door in cosmic terms, our nearest stellar neighbor. These scales reveal humanity's fundamental isolation even in a scenario where intelligent life is common throughout the cosmos. A paradox emerges. The universe may be teeming with life, but cosmic distances make communication or contact practically impossible. Imagine a universe filled with civilizations, each one trapped within their own local bubble of space, unable to reach or even detect their cosmic neighbors. Like cities of light scattered across an infinitely dark ocean, each one brilliant and bustling with activity, but forever separated by unbridgeable distances. Webb simultaneously expands our vision of the universe while emphasizing how tiny and isolated we are within that vastness. Earth is a small planet orbiting an ordinary star on the periphery of a common galaxy in a universe containing trillions of galaxies. If the Milky Way were reduced to the size of Earth, our solar system would be smaller than a hydrogen atom on that scale. If the observable universe were reduced to the size of Earth, the Milky Way would be smaller than the smallest known subatomic particle. These scale comparisons completely transcend human intuition, revealing the inadequacy of everyday concepts when applied to the cosmos. We have no words, no analogies, no mental frameworks adequate for comprehending such vastness. Yet think about this extraordinary fact. Despite our cosmic insignificance in terms of size and location, we represent the only known phenomenon capable of understanding and contemplating these scales. We are matter that has become aware of itself, atoms organized into patterns capable of pondering their own cosmic context. Human consciousness emerges as a remarkable property of the universe. The capacity for organized matter to reflect on its own existence and cosmic context. Through instruments like Webb, humanity transcends physical limitations to observe directly the birth and evolution of the universe itself. Every photon captured by the telescope traveled billions of years through expanding space to be detected by sensors created by a technological civilization. This connection between structures spanning billions of light years and human consciousness on a planet 7,926 miles in diameter is profoundly extraordinary. Consider the improbability of this moment. 13.8 billion years after the Big Bang, matter organized itself on a small rocky planet around an ordinary star in such a way that it became capable of building telescopes. Those telescopes can now observe light that began its journey when the universe was young, carrying information across cosmic distances about the birth of galaxies, the formation of stars, the chemistry of distant worlds. We are literally the universe's way of knowing itself, a temporary organization of atoms capable of deciphering cosmic history through observation and reason. The carbon in our bodies was forged in stellar cores. The oxygen we breathe was expelled by dying stars. The calcium in our bones was scattered by supernovas. We are made of cosmic material that has become conscious. This is perhaps the most profound discovery emerging from Webb's observations. Not just that the universe is vast and ancient and filled with wonders beyond imagination, but that it has organized itself in such a way that parts of it can observe and understand the whole. We are cosmic archaeologists, using light as our tool to excavate the universe's past. Every photon that enters Webb's mirror is a messenger from deep time, carrying news of events that happened when the cosmos was young. We decode these messages using mathematics, physics, and instruments built from elements forged in the hearts of ancient stars. The James Webb Space Telescope represents the culmination of thousands of years of progressively refined astronomical observation through human generations. From the naked eye to optical telescopes, to space telescopes, to infrared instruments at Lagrange points, each advance expanded observable horizons. Our journey began with ancient humans looking up at the night sky and wondering about the lights they saw. They created myths and stories to explain the patterns of stars and planets. They built monuments aligned with celestial events. They developed calendars based on cosmic cycles. Then came telescopes that revealed the Moon's craters, Jupiter's moons, Saturn's rings, and eventually the spiral structure of galaxies. Each new instrument revealed layers of cosmic reality previously invisible to human perception. Photography captured light too faint for eyes to see, revealing nebulae and distant galaxies. Spectroscopy decoded the chemical composition of stars. Radio astronomy revealed invisible cosmic phenomena. Space telescopes escaped Earth's atmospheric interference. Webb represents the latest chapter in this ongoing story of expanded perception. But it's not the final chapter. It's a new beginning in humanity's journey of understanding our position in the immense cosmic tapestry it has revealed. The telescope's discoveries don't provide final answers. They open new realms of questioning. Every observation raises deeper mysteries about cosmic evolution, the nature of dark matter and energy, the prevalence of life, the ultimate fate of the universe. Webb shows us that we live in a universe far stranger, more beautiful, and more complex than we ever imagined. A cosmos where quartz clouds float through alien skies, where organic molecules drift between the stars, where galaxies formed impossibly quickly in cosmic youth, where black holes grew to unimaginable sizes. Yet, for all its strangeness, it's also a universe where the same physical laws operate everywhere, where the same chemistry creates similar molecules across vast distances, where the processes that built our solar system operate throughout the galaxy. We are part of this cosmic story, not separate from it. The elements in our bodies were forged in stellar furnaces. The energy that powers our civilization comes ultimately from nuclear fusion in the sun. The very atoms that enable our consciousness have journeyed across space and time to temporarily organize themselves into the patterns that are us. Webb reveals a universe that is both vast beyond comprehension and intimately connected to our existence. We are made of star stuff, observing star stuff, using instruments made of star stuff to understand the cosmic processes that created star stuff. This is the deepest meaning of Webb's discoveries. Not just that the universe is large and old and full of wonders, but that it has evolved in such a way that parts of it, us, can observe, understand, and appreciate the magnificent whole. Webb's discoveries don't mark a conclusion, but a new beginning in humanity's journey of understanding our position in the immense cosmic tapestry revealed. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.